Hello everyone, thank you for attending this talk. My name is Maaz bin Safir Ahmed, and I will be presenting our work on a new program synthesis-based algorithm for instruction selection on digital signal processors. This work was done in collaboration with Alexander J. Root, Andrew Adams, Shoaib Kamil, and Alvin Jung. Instruction selection is a key phase in any optimizing compiler, whereby expressions in the compiler's intermediate representation are translated into executable instructions from the target platform's instruction set. Unfortunately, when targeting modern vector instruction sets, choosing the optimal sequence of instructions can be quite tricky. Not only do these instruction sets include a rich set of complex intrinsics, but the optimal implementations often require an intricate interweaving of data movement and computation. The traditional approach to instruction selection, and perhaps the most widely used still today, is based on pattern matching. This approach relies on predefined transformation rules to do the translation. For instance, consider the sub-expression in our example that computes the rounding shift right narrow of the input value. To optimally translate the sub-expression, we can add a rule to our compiler that maps this pattern to the rounding shift right narrow instruction in the target instruction set. The problem with this rule-based approach is that not only does it require the compiler developers to have the necessary foresight to generate the correct set of rules, but also that these rules themselves tend to be quite brittle. For instance, here's another expression that computes the same rounding shift right narrow of the input value. While the optimization rule that we just designed worked for the original expression in green, it would not work for this new expression in red, simply due to the syntactic differences between the two implementations. Furthermore, pattern matching often fails to detect context-specific optimizations that require semantic reasoning. Consider the case where the target instruction set does not actually provide the instruction implementing the rounding shift right narrow pattern that we need, but instead it does provide a rounding shift right saturate instruction. A human engineer optimizing the code by hand may realize that the value computed by the shift right operation that forms the input to the cast is always small enough that there is never an overflow or underflow in the cast. This implies that using this instruction that performs a saturating cast instead of a truncating cast does not actually change the semantics of the input code. On the other hand, pattern matching is a syntax-driven approach and does not typically have the capability to do such context-specific semantic reasoning, and will fail to discover this optimization. An alternative approach for instruction selection is called super-optimization. Rather than rely on any predefined rewrite rules, super-optimization attempts to enumerate programs in the target instruction set, searching for one that is both correct and has the lowest cost. Although this approach can generate optimal implementations, it has limited scalability due to the combinatorial complexity of the search problem. Therefore, to scale to larger programs, state-of-the-art super-optimizers typically use a sliding window decomposition. Since the entire program or expression may be far too expensive to optimize together, they restrict each optimization query to a small window of instructions that are then optimized locally. Sliding window decomposition allows super-optimizers to scale to arbitrarily large programs, but it is not well suited when performing instruction selection on modern vector instruction sets. First, modern instruction sets contain complex intrinsics that implement patterns of up to 15 or even 20 operations. These patterns are actually larger than the window sizes used by many state-of-the-art super-optimizers. Second, even if the window sizes were large enough to contain these patterns, there is no guarantee that the entire pattern will actually fall within the same optimization scope. Since each window is optimized locally, the super-optimizer may not detect opportunities to use these powerful instructions if the pattern is split across adjacent windows. Finally, the sliding windows are an arbitrary grouping of instructions and provide no semantic insight into what each code block does. Lacking any insight, the super-optimizer then has no choice but to search the space of all possible instruction sequences that it can generate. This brings us to RAKE, a new, scalable, synthesis-based algorithm for instruction selection. The key observation behind RAKE is that rather than decompose expressions into arbitrary windows, what we really want to do is group operations that together implement a higher-level compute pattern. For instance, we can decompose this input expression into these two groups, where the first group implements the higher-level rounding shift right pattern, whereas the second group implements the higher level multiply add pattern. Decomposing in this way has several advantages. For starters, the size of each group is elastic, and we avoid those instances where the pattern that could have been implemented as a single instruction is now being split across multiple optimization scopes. Secondly, the decomposition exposes higher level semantic information about each group of operations. We can use this information to refine our search. For instance, when synthesizing an implementation for this rounding shift-right subexpression, we can restrict the synthesizer to only consider the subset of intrinsics from the target platform that perform relevant operations, such as any shift-rights, rounding, casting, or addition intrinsics, and ignore all other irrelevant intrinsics that do things like vector reductions, or I/O operations, or compute a histogram. Implementing this kind of semantic space decomposition requires two things. First, we need to identify what are the set of high-level compute patterns that we want to base our clustering on. And secondly, we need an algorithm that actually performs the clustering. In RAKE, we derive the set of high-level compute patterns from the target instruction set as a set of Uber instructions. One of our key observations when designing this instruction selection algorithm was the fact that most vector instruction sets contain a large number of very similar instructions. For example, here's a subset of instructions provided by Qualcomm's HVX architecture. We have the add instruction that adds the elements of two vectors together. We have the multiply add instruction that multiplies the elements of the first vector by a constant before adding it to the second vector. And then we also have the multiply add instruction that multiplies the elements of both vectors with a scalar before summing the results together. If we rewrite these expressions slightly, it's obvious that both the add and the multiply add instruction implement a specialization of the more general to multiply add pattern. In fact, we can view all three of these instructions as a specialization of the even more general n multiply add pattern. And it gets worse. In the full instruction set, for each of these instructions shown here on the slide, we have multiple variants for handling different integer types. We also have variants for widening and non-widening arithmetic, and we even have variants that specialize for different input data layouts. Given an instruction set such as this one, we first identify the set of instructions that have similar or overlapping semantics. Then, for each set of intrinsics, we define a single function that implements their common higher level pattern. We refer to this unifying function as an Uber instruction. For example, we can unify all the shift-right intrinsics by defining a single function as follows. This shift-right Uber instruction has flags to specify the optional rounding and saturation to a lower precision, as well as a flag to specify whether we want to compute a logical or arithmetic shift. Similarly, we can unify all multiply add instructions by defining this Uber instruction that takes a weight matrix and convolves the input vectors with the provided weights. By providing different weight matrices, we can use this Uber instruction to implement any sequence of multiply add operations. Once we have derived the complete set of Uber instructions, which we refer to as the Uber instruction IR, we can reframe the original code decomposition problem as a code rewrite problem. In other words, we can decompose the input expressions by rewriting them using the Uber instruction IR. This gives us a two-stage algorithm for instruction selection, where first the input expressions in the compiler's IR are lifted to the higher level Uber instruction IR. Then each Uber instruction in the lifted expression is lowered to an optimal executable instruction sequence in the target ISA to generate the final expression. The first lifting rewrite is performed using a greedy operator packing algorithm that resembles traditional instruction selection approaches such as maximal munch. The key difference being that we do not rely on predefined rules, but rather query a synthesizer at each step to determine when operators can be folded into the same tile. To understand how the lifting algorithm works, let's apply it to our running example. There are three steps to the algorithm: fold, replace, and extend, that are applied repeatedly until the entire expression is lifted, starting with the first operation. Given the cast operator in the input expression, the first step is to try to fold this operator into the last Uber instruction in the lifted sequence. Since the lifted sequence currently has no Uber instructions, we move on to the next step, which is replace. In this step, we try to replace the last uber instruction in our lifted expression. Once again, since there is nothing to replace yet, we move on to the third and final step, extend. In this step, we try to synthesize a new uber instruction that can represent the semantics of this operation and add the synthesized uber instruction to our lifted expression. The synthesizer returns the cast uber instruction with the round and saturate flags set to false. Now, with the cast operation lifted, we move on to the next operation in the sequence, which is the shift right operation. The first step is to try to fold the shift right into the last uber instruction in the sequence, which is the cast uber instruction. This can be done, for example, by flipping the round or saturate flags. Since this is not possible, we then try to replace the cast uber instruction with a different uber instruction that can represent the full sub-expression. The synthesizer returns the shift right uber instruction with the narrowing flag set to the saturating narrow flag set to true. Note that the synthesizer is able to reason when this is or isn't safe to do. We move on to the next operation, which is the addition by 8. This can be folded into the current uber instruction by simply flipping the round flag. This process then iteratively continues and greedily folds as many operators it can before adding a new uber instruction until all operators have been lifted, giving us the final expression, which is a shift right instruction followed by a vector scalar multiply add instruction with the weight matrix of 1, 1, and 2. Since this is a greedy algorithm, it does not guarantee that it will find the shortest sequence in the uber instruction IR. However, the uber instruction IR, unlike the target instruction set, is much higher level, making it much easier for the greedy algorithm to converge on the best representation. Furthermore, the greedy algorithm is scalable, which is important as the input expressions may be arbitrarily large. Once the input expression has been lifted to the uber instruction IR, we use exhaustive search guided by a cost model to lower each uber instruction to the target instruction set. A key challenge while lowering is that to find the best performing implementations, we must explore implementations that contain both computation as well as data movement. Powerful fused intrinsics offered by modern architectures are often restricted to certain input and output data layouts. For example, on this slide, you can see the VTMPY instruction from Qualcomm's HVX architecture. This instruction is extremely useful for implementing 3-element wide sliding window reductions. The color scheme highlights the flow of data from the input vectors at the top to the output vectors below. Notice that not only does this instruction have a really unusual read pattern, but it also produces output in a deinterleaved format. Using such instructions often requires swizzling either the input data into the right layout or the output data into the right layout, sometimes even both. And the increased throughput offered by these instructions can actually justify the overhead of the introduced data movement. Therefore, during the lowering stage, RAKE decouples the synthesis of computation from the synthesis of data movement. This is done by first synthesizing a swizzle-free sketch, which is a partial implementation that uses concrete intrinsics to represent computation, such as the vadd instruction, but uses special constructs to represent arbitrary data movement. This decoupling allows RAKE to scale and explore a much richer set of implementations. In this example, we have a swizzle-free sketch that uses the fused HVX instruction to perform the rounding saturating shift right narrow operation. However, since the instruction produces interleaved output, we must deinterleave the input vectors to undo the implicit interleaving and get the output in the right format. When synthesizing swizzle-free sketches, we represent data movement using a hash table that maps each lane of the swizzle vector to the input value it must contain. In other words, to prove that the sequence of compute intrinsics can produce the correct output, we synthesize a data swizzle over which the output is correct. Figuring out how this data shuffle can be implemented optimally using the data movement intrinsics that are available in the instruction set is deferred until later. Synthesizing these hash tables to represent data movement is much easier than synthesizing the optimal swizzle instruction sequence, since it can be done incrementally. For example, rather than compare the entire outputs of the synthesize and the input expression, we can, as a filtering step, compare just the first 4 elements of the generated output vectors. This is a necessary condition for correctness and will fail for the vast majority of obviously wrong candidates in the search space. To prove this necessary requirement, we only need to synthesize the hash tables that describe what data must be contained in the first two elements of the Swizzle's input vectors. Synthesizing such tiny hash tables is cheap and allows us to quickly eliminate the vast majority of completely wrong candidates. One challenge of this decoupled approach is that when synthesizing swizzle-free sketches, we can only generate the cost lower bounds, which is essentially the cost of the compute intrinsics, as we do not yet know what the cost of the necessary swizzles will be. The sketch with the smallest cost lower bound may not necessarily yield the implementation with the lowest final cost. Therefore, we allow our algorithm to backtrack, using the cost of the generated implementations as a constraint to refine the search space and generate better implementations, until a better implementation can no longer be found. To evaluate our instruction selection algorithm, we compare the runtime performance of 21 benchmarks, generating a total of 450 expressions. These benchmarks include common image processing operations such as blurring or edge detection. It includes the Franken camera pipeline, halide implementations of various TensorFlow layers, quantized matrix multiplication, among others. As a baseline, we compare against halide's highly optimized HVX backend, which uses a combination of LLVM's instruction selection and superoptimization, and also a corpus of handwritten rules written by Google and Qualcomm engineers over the years to fill in the gaps of the LLVM optimizer. It must be noted that for all of these benchmarks, we use the exact same high-level schedule for both implementations. The only difference between the two implementations is the instruction selection algorithm. Here is a graph that summarizes the results of our experiments. On the y-axis, you can see the speedup observed by our instruction selection algorithm over the halide's HVX optimizer. On the x-axis, you can see the various benchmarks. As you can see, for 10 out of the 21 benchmarks, our instruction selection algorithm performed better than halide's optimizer by a non-trivial amount. Another 10 benchmarks showed identical performance. Only one benchmark performed slower than before. Upon further investigation, we realized that this was not due to worse instruction selection, but rather because halide's instruction selector has the ability to alter scheduling decisions, like the intermediate layout in which the data is stored. This is done to enable better instruction selection. This sort of optimization is currently outside the scope of RAKE. Overall, the mean speedup observed was 18% across all benchmarks, and the mean compile time was 62 minutes per benchmarks. Our instruction selection algorithm not only demonstrated the capability of translating large input expressions, such as this expression taken from the Franken camera pipeline, but it also demonstrated its capability of generating very long sequences of instructions. For instance, this synthesized HVX expression from the quantized matrix multiplication benchmark consists of 103 HVX intrinsics, and overall, this benchmark performed 70% faster after optimization. Moving forward, the most important question we want to ask is whether we can memoize the transformations that we have discovered through RAKE. Despite our many optimizations, synthesis remains an expensive process. Effective memoization could mean that we do not have to use synthesis for patterns that we have already optimized before. In addition, we are also actively working on extending RAKE to support other vector instruction sets, notably ARM and AVX2. Though this is still ongoing work, early results indicate that the set of Uber instructions required for these instruction sets are remarkably similar. To sum up this talk, we present a new instruction selection algorithm called RAKE that lifts input expressions into an Uber instruction IR before lowering them to the target instruction set. RAKE decouples the synthesis of computation and data movement to make the lowering phase tractable. Our results show that RAKE can outperform halide's professionally developed instruction selector by an average of 18% across 21 real-world benchmarks. Thank you for your time, and now I will take any questions that you have.